welcome back to our last session. Yesterday we were discussing about divisors, principal divisors. We defined also the genus of a function field, and at the end we were able to put all the ingredients together to define algebraic geometry codes. So today, to end, we are going to study a bit about that algebraic geometry codes. What can we say about the parameters of that code? And then we'll see, we'll return to our asymptotic problem that was about getting long sequences of long codes, sequences of codes such that the parameters, if I see the relative parameters of those codes were something good, which means non-zero. So, I didn't say it yesterday, but algebraic geometry codes were introduced by Gopa in this work. Codes on algebraic curves. This is in 1981. And as we said yesterday, this was a generalization of Reed-Solomon code. So I'm going to write again, as I did all day, for Reed-Solomon code. We start with a finite field, FQ, consider the multiplicative group, alpha 1, alpha q minus 1. Then we define the set of polynomials of bounded degree k minus 1, f of x, a polynomial with coefficients on fq such that the degree of f was less or equal than k minus 1. And so the Reed-Solomon code was just the evaluation of polynomials inside this space in all the elements of fq star. F alpha 1, f alpha q minus 1 for an f in Lk. And so for HG codes, we, instead of working on a finite field, we work over a function field defined over the finite field fq. Let f over fq a function field. And so instead of using all the elements in the finite field to set it as our evaluation set, we just pick n rational places and places of degree 1 on the function field, P1 up to Pn, and different rational places of f. Rational means of degree 1. And to get a space in which we are going to pick our functions to evaluate, we need another divisor whose support is doesn't contain all of these places. So let G another divisor of f such that the support of G and the support of the divisor that I call D, which is the sum of all the rational places, P1 plus Pn, has nothing. And so instead of using this set, we use the Riemann-Roch space associated to G that we defined yesterday, where all the elements of the function field such that the principal divisor of that element was greater or equal than minus the divisor, and the zero, of course, we want a vector space. And so with that, the AG code was defined. I'm going to write it here so we can have it next to the Reed-Solomon code. C sub al of, I put DG to make emphasis on that this D is the sum of the places, the evaluation set, and this is the other divisor, and this was x of P1, C of P1, C of Pn, such that C is on the Riemann-Roch space. So the comparison is evident. It's easy to see why this generalized this other code. And so now what we want is, first to see that this is defined correctly. So I need to say why all of these coordinates are inside FQ, because I want a code over FQ. And then what I need is to say something about the parameter. We have studied already the parameters of the Reed-Solomon code. We said something about the dimension, the minimum distance, and we will try to do the same with this setting. So, first of all, if we have a word in the AG code, so we have an element in the Riemann-Roch space, and we see this code word. The first thing that we see is that since Z belongs to this space, and this space was the set of elements such that the principal divisor of Z was greater or equal than minus G, then this condition is the same as saying that the valuation for every place on the function field of Z has to be greater or equal than minus the valuation of the divisor. And so if I choose this place to be one of the places in the evaluation set, if Q is equal some pi, what I have from this condition is that the valuation at pi of C is bigger or equal than the valuation of this place on G. And since pi is not contained in the support of G, this valuation is 0. So what I have is that this valuation is bigger or equal than 0. And if you remember our second session, we saw that the elements such that the valuation was greater or equal than 0 belongs to the valuation ring. So Z belongs to the valuation ring associated to the place pi. And this is saying that when I want to see the residue class of pi, remember that we define this thing to be Z mod pi if Z was in the valuation ring, or infinite if it was outside. So this thing actually belongs to fpi. It's not an infinite element. But that's not enough for us because we want this to be a word of fq to the n. And now we have to use that the place is a degree 1 place. Recall that the degree of a place was defined to be as the degree of the extension of the residue class field over the final field. So if pi is a degree 1 place, that means that this is a degree 1 extension. So I can identify all the things here as element of fq. So actually, I can see this residue to be an element of fq. And therefore, I will have that all the words I'm defining on the AG codes are words inside n copies of fq. So I'm having things there. And of course, because of how I have defined this, and this is a vector space and everything, then this defines a linear code and everything that I wanted. I just have to say something about the parameters that I don't know. But this definition now, I can see that it is well defined. It is a code. So CL of dg is actually a linear code over fq. And so let's see what happened with the parameters. So we have this theorem that if the AG code associated to divisors D and G is an NKD code. Remember that we said that was an NKD code if N was the length, K was the dimension, and D was the minimum distance. With K equals the dimension of the divisor G minus the dimension of the divisor G minus D. And the minimum distance is bounded by N minus the degree of the divisor G. So actually, the parameters of the AG code depends on the divisor that I'm choosing to evaluate here, of course. It's what we thought it should be. So how do we prove this? Well, first we have to see that, well, this code was actually the image of the evaluation map. We define the evaluation map from the Riemann-Roch space. I will put just to the code. So this way is surjective. This is inside fq to the n, of course, such that for each function in the Riemann-Roch space, I get the evaluation in the elements of in the support of D. And so this is a linear map. And what about the kernel of this map? Well, if a word is sent to the 0 coordinate, so if I have this element such that C of P1, C of Pn is the 0 element, that means that all of this element Z belongs to Pi for all Pi, because recall that this is 0 if and only if this element belongs to the ideal, and so the residue modulo pi is 0. And so if we had that C belongs to P1 or to all the PIs, then that means that P1, P2, all of them are zeros of the element Z. And so C belongs actually to the Riemann-Roch space of G minus D. So this is actually L of G minus D. Recall that we said, well, if this is an effective divisor and this is an effective divisor, what we have was that the positive part was telling me more or less the poles of the elements where lives, and the negative part were saying, well, this element needs to have at least zeros on these elements. So these things is saying me that Z has a 0 in P1 and a 0 in Pn. So it belongs to this space, and therefore we had the first thing proved. Because now, if I say I know which is the dimension of the kernel, of course I have that K, which is the dimension of the code. Sorry. In this map, the evaluation here is going to be the dimension of the domain, the L of G, minus the dimension of the kernel. So this is going to be the dimension of L of G minus the dimension of the kernel of the evaluation map. And this is exactly L of G. This is how I define the dimension of a divisor as the dimension of the Riemann-Roch space associated to that divisor, and the dimension of the kernel is the dimension of the Riemann-Roch space L of G minus D. So here I have minus L of G minus D. So we have our statement for the dimension of the code. Now we want to see that the minimum distance of the code satisfies that is bigger or equal than n minus the degree of G. So we are going to assume that we have something non-zero inside the code, because if we have only the 0, then we don't care. We don't have a minimum distance there. So assume that C sub L of the G is not only the 0, and let's see be an element of L of G such that this element realize achieve the minimum distance. So such that we have a word in the code of minimum distance D. So C of P1, C of Pn has weight equals D. Recall that when we, in our first session, we said that for linear codes, the minimum distance was exactly the same as the minimum weight, where the weight of a word was defined as the number of non-zero elements inside the word. So if I said that this word has minimum weight, has the minimum attains the minimum distance of the code, then what I'm saying is that in this word I have D non-zero coordinates and n minus D 0 coordinates. So this word has n minus D 0 coordinates. And so let's assume that the 0 coordinates are on the places P1 to pi n minus d. So if these elements are zeros of Z, then we have, exactly as we did before, that Z belongs to L of G minus pi1 plus pi n minus d. Because of course, if this element has zero, this p1, pn minus d are zeros of the word, and these places do not belong to the support of G, then I can remove it from the space and still happening this. If you cannot see it at once, then you can also write the evaluations at a place which is on the support of G and a place which is one of these, and you see that this is actually what we got. Remember that zero coordinates means that the evaluation as this Pij of Z is bigger than 0. And so if we have something, a non-zero element, if we have a non-zero element inside this space, it's because this space is not only the 0. And we had a result that says that if the degree was if the degree of the divisor was greater than 0, greater or equal than 0, was less than 0, if the degree of A was less than 0, then L of A was only the 0 element. So if this is not the 0, it's because the degree of this divisor is greater or equal than 0. So I'm using the other way around. If this is not happening, then this is not happening. So the degree of this divisor, G minus pi1 plus pi n minus d, has to be greater or equal than 0. And from that, I have what I wanted. Because the degree of that divisor is the degree of G minus the degree of the sum of the pi's well, the degree of G is the degree of G. And the degree of this divisor, since each of these are places of degree 1, is exactly n minus d. And therefore, the minimum distance is greater or equal than n minus degree of G. And this is what I wanted to prove. So we said degree of P equal 1 for all I. Yes. To build our AG code, we need to start with n rational places, n places of degree 1. We need that to evaluate, because that way we know that our coordinates are inside FQ. So you must start with n rational places of degree 1. And that's one of the greater questions of the theory, is how many of these rational points, rational places, can I get inside a function field? And that is something that we are going to see after we finish this in a few minutes. And the problem of finding enough rational places in order to have long codes, because remember that for the asymptotic problems, we want that the length of the code tends to infinity. So I need to build somehow function fields in which we had a lot of rational places. And I have to see if that is possible or not. So this is about the parameters, but we have a corollary of these results because, well, now I know that the dimension is exactly the dimension of G minus the dimension of G minus D, but what do I do with that? How do I compute these things? And so we are going to use Riemann-Roch theorem to say something else about this. So the corollary is now assume or suppose that degree of G is less than n. Of course, our bound for the minimum distance is n minus degree of G. If I get a G such that the degree is greater or equal than n, then the bound for the minimum distance is trivial. I always said that the minimum distance is greater or equal than 0, of course, but can I say more about this? Well, this is going to have some something to say if n minus degree of G is bigger than 0. And so this hypothesis is not asking that much. It's saying, well, I want this in order to have a non-trivial bound for the minimum distance. So in this case, the evaluation map is injective, and we have the following. Well, first, that the code is an NKD code with, in this case, K is going to be equal the dimension of the divisor G only, and therefore, using the Riemann-Roch theorem, I can say that this is bounded by below by degree of G plus 1 minus the genus of the function field. Well, and of course, the minimum distance is greater or equal than D minus degree of G, which is a non-trivial thing. Here is where G is the genus of the function field in which I have defined the code. In particular, if we add these two parameters, what we have is that K plus D is greater or equal than N plus 1 minus G. But I can say something more. If, moreover, I have not only that the degree of G is less than n, but I have also that the degree of G is greater than some constant involving the genus, if you remember the last theorems that we saw, then I can say that in this inequality, I have equality actually. Recall that when we have that the degree of G was greater than 2C minus 1, where G was the genus, then this was an equality. Because if not, I had something more here that was the dimension of that divisor with the canonical divisor that we did not define. So the second part is if in addition, I have that 2g minus 1 is bounded the degree of g, then k is actually, the dimension is actually L of g, there is a degree of g plus 1 minus the genus. And the third part is coming from the classical theory of codes. If we have a base if we are in this case and we have a basis for the Riemann-Roch space of G, if x1 xk is a base, this is well, let's put it here because it is with this same hypothesis, right? Moreover, if this is a base for L of G, then a generator matrix for the code is putting all of the evaluation of these functions on the evaluation set. So I have x1 of p1 up to x1 of pn, x2 of p1, yes, up to x2 of pn, and the last one is going to be xk of p1 to xk of pn. This is a generator matrix for the code. And so the only thing that we have to prove here to have this corollary is that the evaluation map is injective. If we have that, then everything is already achieved for using other theorems or other results. If I had that the evaluation map is injective, then if I say the theorem that says that that the dimension was L of G minus the dimension of the kernel, but if it is injective, the kernel has only the 0, so the dimension is 0, and so we have this equality. And for the Riemann-Roch space associated to G, we know that the dimension, and this is for Riemann-Roch theorem or a consequence of that, we know that this is bigger or equal than degree of G plus 1 minus G. This is just adding these two things. And if we have this, then this was the bound that we needed to assure that the Riemann-Roch space was actually this quantity and was not bounded, because in that case we had that if the Riemann-Roch space was equal to this, and I have here another term involving k minus g, where k was a canonical divisor. So this is not here when degree of g is greater than 2g minus 1. And so we have what we want. And this is for classical theory. If I get a basis of the evaluation space, then I put all the elements in rows and I get a generator matrix. So let's just see why the evaluation map is injective in this case, which is really one word that we have to say about that. We prove in the theorem that the evaluation map we prove that the kernel of this evaluation map was actually L of G minus D. And this is all that I have to know, because we saw that if the degree of, the degree of a divisor was less than 0, then L of A was only the 0 element. And if I'm assuming that degree of G is less than n, then the degree of G minus D is the degree of G minus the degree of D, but the degree of D is exactly n, and therefore this is the negative degree divisor, so the Riemann-Roch space associated to this is 0, and so the kernel has only the 0, and this is injective, and everything happens in this corollary. Okay? Please let me know if I am speaking too quickly or going through these results very quickly, okay? I can go back and say again, but slower. So please let me know. So remark here, one word that I want to say is that, as I said, in this case, when the degree of G is strictly less than n, we have this bound for the dimension, and so we have that K plus D is greater or equal than n plus 1 minus the genus. This is if degree of G is strictly less than n. But we always have the singleton bound that we saw in the first session that says that the dimension plus the minimum distance cannot go over n plus 1. And so what we have for algebraic geometry codes such that the degree of G is less than n is that if the genus of the function field is 0, then the code that I get is an MDS code. If G of f is equal to 0, then the AG code, the AG code is an MDS code. So in that case, we have that the dimension plus the minimum distance is exactly the length plus 1. And that was the case for Ricci-Solomon codes. And of course, we can recover this situation of Ricci-Solomon codes using, for example, the rational function field, the example that we were working. And if I choose, as we did yesterday, the divisor G to be R times the place at infinity, the P infinity, which was the element such that the degree of the numerator was less than the degree of the denominator, then the Riemann-Roch space was the space of polynomials of the same that was used for the Ricci-Solomon codes. And in this case, I get if D is P alpha 1 plus P alpha Q minus 1, then I get exactly the representation of Ricci-Solomon codes as AG codes. And since the rational function field has a genus 0, I recover the MDS exactly. The Ricci-Solomon codes are MDS codes because this is exactly n plus 1. Okay. Well, one more thing that I want to say about this, the parameters of these codes before we go to the asymptotic part again, is, well, we have one more result about when we will have that the degree, the minimum distance is exactly n minus the degree of g. And so we have this proposition that you see that all of these results are really easy to prove. So we assume that the dimension of the divisor G is positive. And so what we have is that D is exactly n minus degree of G if and only if we have another divisor D divisor, I will call it D prime, such that it's comparable with our divisor D. So since D is a sum of places of degree 1, then D prime is going to be also the sum of those places, because if I want to compare them, the support of one has to be inside the support of the other. So the support of this has to be inside the support of D prime has to be inside the support of D. So actually, if D is a sum of n rational places, then D prime is going to be the sum of some of them. With degree of D prime equals to degree of G. And of course, we are L of G minus D prime to have something inside. And so let's start with the part that we assume that the minimum distance is exactly n minus degree of G. And let's prove that we have a divisor D prime with these conditions. So we go this way. Assume that D is exactly n minus degree of G. So since my hypothesis is that the Riemann-Roch space has a positive dimension, then I can pick an element there, a non-zero element, inside the Riemann-Roch space associated to G, such that this minimum distance is realized. Let's see a non-zero element in the Riemann-Roch space, such that the minimum distance is realized, which is that the weight of the word using this C is exactly D. Weight of CP1 until CPN is exactly D. And so, as we did before, since this word has D non-zero elements, then that means that has n minus D zeros, n minus D zeros. And the zeros of this word are going to be some of the places involved in the divisor D, that I'm going to call it, as before, PI1 to PI n minus D. And so that is the divisor D prime that I'm picking, is the sum of those places. So now, if I define D prime to be the sum of these elements, 1 plus pi n minus d, where I have that this is an effective divisor, and of course is less or equal than d, because I'm not taking all of them, but n minus d of those. And the degree of this divisor is n minus d, n minus d. But since the minimum distance was exactly n minus the degree of g, this is exactly the degree of g. Here I'm using the hypothesis that d is equal to n minus degree of g. And of course, this element c belongs to L of g minus d prime. And so, since it was a non-zero element, the dimension of g minus d prime is positive. And so I have this, effective divisor with this hypothesis. Now, if I go in the other direction, now I'm assuming that I have a divisor d prime such that the degree of the divisor is the degree of g, and that this space has a non-zero element. So we're going to pick C, a non-zero element inside L of g minus d prime. And so if it is here, I go the other way around. C is going to have degree of d prime zeros in the support of d. So if I pick this word, C of P1, C of P n, since z belongs to this space, n minus d of these coordinates are going to be 0. Remember that d prime is formed with some of the elements of some of the places of d. So I have n minus d places in the support of d which are zeros of z. And so if this word has n minus d zeros, then it has d non-zero coordinates. And so the weight of this word is exactly this, d. And since for any AG code I had that the minimum distance was always greater or equal than, well, sorry, not d, because I don't know which one is d. This has exactly the degree of d prime n minus the degree of d prime non-zero element. Since the degree of d prime is the degree of g, this word has weight n minus the degree of g. And now, since I always know that the minimum distance is greater or equal than n minus the degree of g, and I have found a word inside the code that has exactly this weight, then the minimum distance has to be this, n minus degree of g. And so I end it. Okay, so in this other case, let's go it through again. Since this space has dimension bigger than 0, then I can pick a non-zero element inside this Riemann-Roch space. If I have a non-zero element inside this Riemann-Roch space, it means that z belongs to L of g, of course, because it's there. This is inside L of g. So z belongs to L of g, and also that z has degree of d prime zeros in the support of d. And so the weight of this word, which is the amount of non-zero coordinates, is the amount of coordinates, which is n, minus the amount of zeros, which are degree of d. But my hypothesis was that degree of d prime was exactly the degree of g. So this word has degree n minus degree of g non-zero coordinates. And so since the minimum distance is bounded by below by this quantity, and I have a word that realizes that attains exactly this quantity, then this has to be the minimum distance. So this is everything about how to build an AG code And what can I say about the parameters? And of course, to use this kind of codes, we need to know something about the Riemann-Roch space of the divisor G. So that's the difficult part of the theorem. Try to build a basis for the Riemann-Roch spaces. First, if we bound the degree of the divisor G, then we can set something about the dimension of that space. And knowing the dimension of that space is going to give us more information to know how to get linear independence elements inside there to build the base. But it's not always easy to compute the exact dimension of the Riemann-Roch space if we are away from these places, away from degree of G, away from 2 genus minus 1 and n. If I go to one of the sites, then I don't know what to do with that. I have bounds, but I cannot compute it exactly. And once I know the exact dimension of the Riemann-Roch space, then I had to build a base for that, and with that I will be able to compute the words inside the code. In some examples, what we do is just, well, we compute the dimension and then we start looking for elements, evaluating elements there, and when I found an element, I put it on the base, and then I start computing other elements inside there, and if the second element that I built is linear independent with the first one, I add it to the base, and it's not, I continue looking up to I complete the base. So there are many cases in which bases are known, but many other cases in which we still need more work to do. We don't have an algorithm to say, well, you give me your divisor and I will give you the base for all the cases. Okay, so that's an interesting problem that we can try to solve, or to solve in some cases, for example. But I'm not going to go into that direction because, as I said, I wanted to say something about the asymptotic problem. So let's have a 10-minute break, and when we resume, we will end with the asymptotic problem, and that will be all. Thank you. Well, now we will get back to the asymptotic problem, but first I had a question about if I could give an example of a sequence of HG codes that is asymptotically good. Then I don't know if I'm going to have time to say something about this, exactly how to build a sequence, an explicit sequence. But if you want, I can give you a reference of a work of myself with Ricardo Podestá and Ricardo Toledano. This is a work published in Design Codes and Cryptography last year. And in this work, we built asymptotic sequences of codes using towers of function fields that are infinite sequences of function fields, one inside the other one, and we built a code in each of that extensions such that they are asymptotically good, and also we give some examples of block transitive HG code, so we are having more structure, not only linear HG codes, but with some other structure for the elements for the code, the coordinates of the code word. And of course, there are many others. This is one of mine, so that's why I'm saying that to you. So now we will get back to the asymptotic problem again. And so we saw in our first session that a problem was to see if I could get a sequence of codes such that when I say the sequence of relative parameters, call that the relative minimum distance, was defined as the equation between the minimum distance and the length of a code if each of those was a Ni, Ki, Di code over the same FQ. And the information rate was the equation between, or the comparison between the dimension and the length. And so we said that a sequence was asymptotically good is these two things when we saw the limit of this with I tending to infinite, and this was a sequence of different codes. If that limit was greater than 0, then we said that the sequence was asymptotically good. So what we saw is that if we did not know about where the limit points of the parameters of sequences of codes were, but we have some bound with that Manning functions that says that, well, is already what we already saw, that these three were upper bounds, so the Manning function was somewhere here, and we had one lower bound, which was the Hilbert-Bardsham bound. So actually, the Manning function was something in between this. And so what we saw is that with classical codes, with classical theory, we cannot get something better than the Hilbert-Bardsham bound. If we try to build a sequence of codes and see the relative parameters, the sequences of relative parameters, we can only get up to this bound given by Hilbert-Bardsham. So the thing is that with these other codes, with HG codes, we can have something that it is better in some interval that I'm going to show you at the end. So the first thing that we need is to know, well, as I said, to build an HG code, I need to have a great amount of rational places, of places of degree 1. So can I get a sequence of function fields such that the amount of rational places grows a lot? So the question is if I can get enough rational places in order to define enough HG codes. And so if we have f a function field over fq, and we define by n of f the number of rational places, the number of places on f of degree 1, I want to see how big this number can be. Can I build really a lot of, can I have a lot of rational places here? Remember that for the Reed-Solomon code, the problem was that the length of the code was always bounded by the size of the finite field. So I could not get more than that. I could add 1 point or something, but I cannot beat a lot that bound. So if I wanted to build a really big, long code, then I would need a finite field really big, a really big finite field. But in this case, we have the Hasse-Weil bound that tell us that, well, actually, if we let the genus of the function field grow, if we stay on the genus 0 case, then we are going to be tied to the size of the field. But if we let the genus grow, then we can have more rational places there. This is the Hasse-Weil bound. And it says that the number of rational places on a function, and here denotes the number of rational places of a function phi f, satisfies that is less than 2g, the difference with the amount of points q plus 1 is bounded by this. And so in the case of genus 0, as I said, when I'm on the rational function field, for example, this, I get a 0 here, and so I see that it cannot go farther. I have, like I said, like we saw in the case of the rational function field, we have q plus 1 rational places, and that's all. In the case of f being fq of x, we saw that the only rational places there were the ones associated to x minus alpha, where alpha was an element of fq, and the one at infinity. And that's all the rational places I can have. I have only q plus 1 rational places. But if I let this g grow, then I can have more things inside here. And there are some improvements. One due to Serre. Can you see these colors? Yeah. That says that actually we can put g times the integer part of 2 to the q plus 1. So we have another definition now to study what happened with the relationship of the rational places, the maximum amount of rational places a function field of genus G can have if I let the genus goes to infinity. If I let the genus grow, what happened with the amount of rational places? And that is studied with the Ihara constants. This is a definition. Well, it's called Ihara constant or Ihara function. A of q. And is defined as now the lim sup for g going to infinity of nq of g over g, where here nq of g count the maximum number of rational places that a function field of genus G over fq can have. So this is the maximum number of rational places of a function field where f is a function field over fq of genus G. So I pick the genus and I say, well, which is the maximum amount that it can have? The maximum amount of rational places there. Then I change the genus, I go to a bigger genus, and I compute the maximum amount. And so I get this, this constant. So what can I say about this? Is this bounded? Is this zero? Is this something not zero? Well, of course, if we use the Hasse-Weil bound, what we see is that this thing is bounded by 2 times q to the 1/2. And this is always a non-negative number. But we have some results that says a bit more about this Ihara constant. And one is the bound by Bloodwood and Drinfeld that was also achieved by Chara independently. The theorem is that actually that constant A of Q is bounded by Q to the 1/2 or square root of Q minus 1. And this holds for all Q, and also this is Bloodwood. And also we know that this actually is never 0, is bigger than 0, because Serre proved that there is a constant, and it is a specific constant, a constant C, such that for all Q, this is bigger than C log Q. So we know that this A of Q lives between something here and the square root of Q minus 1. And so another interesting problem is finding the values of this thing, because we don't know it in all the cases. But we do know it in one specific case. And it is when if Q is a square. If Q is square, then we not only know that it is bounded by this quantity, this is an upper bound, but this quantity is also a lower bound for A of Q. So in that case, in the case of squares elements, we have exactly the value of A of Q. In this case, we know that this is square root of Q minus 1. Or if you want, A of L squared is exactly L minus 1. And there are many bounds. There are some bounds for the case of Q being Q. There are also lower bounds for specific prime cases. For example, for Q equal 2, equal 3, equal 11. For the first primes, we have some bounds, but the actual value is not known. And sometimes some couple of years we see a new work in which the lower bound was improved by a really little number, so we may think that that's going to be the actual number or not. So another problem is finding lower bounds for this quantity. And what does all of this has to do with the codes? Well, the thing is that if we can find a lower bound for this Ihara constant, then we have a lower bound for the Manning function. And that's why we care about this. This proposition is not hard to prove, and actually I was first planning to do the proof of this, but I think I'm going to let you know just the steps you have to follow to prove it. It's on Stichter's book if you want to see it, but so we can talk a bit more about the results. So suppose that you know that A of Q is bigger than 1. So you can get a lower bound for Manning function using this quantity A of Q. In the interval 1 minus 1 over A of Q. I recall that this Manning function was the one that it was a continuous function that was 1 at 0 and 0 for the last part of the interval, and we know that was decreasing on the rest, but we did not know. And this function was the one that was, if we have that B of Q was the set of relative parameters of a code, and delta was delta of C for some code C over FQ. And then we know that the set of limit points of B of Q was actually the set of elements R delta, such that delta was between 0 and 1, and R was bounded by this Manning function. And so this is what we wanted to compute, to say something about. And now with this, if we can get a lower bound for the Hara function, then we can get a lower bound for the Manning function, and we actually have a sequence of codes attaining this bound. So to prove that, the steps that you have to follow to prove that is you will construct a sequence such that the number of rational places on a function field over the genus of a function field, you will build a sequence of function field such that this tends to A of Q. This is because of the definition of N of Q. And so the codes that you are going to build are using D, all the elements on this set, all the rational places here, except from one. And so that one that I'm removing from there, I can use it to build the other divisor for the Riemann-Roch space. And with that, we get that, well, I could put Ri of something here, the one which is left, Qi. And using these divisors, we get the sequences of codes. And this, when we study the parameters of these codes, we are going to have that this sequence is asymptotically good, and the bound is going to involve this quantity as we see here. Actually, what we are going to get is that if we choose these elements here such that if we pick an element between 0 and 1 minus 1 over A of Q, and we have this Ni over Gi tends to A of Q, and we pick a sequence Ri such that Ri over Ni tends to 1 minus delta. And so with that, the dimensions of these codes that I constructed are bigger or equal than Ri plus 1 minus the genus of the function field, and the minimum distance satisfies that are Ri minus Ri. And using this, you get exactly what you want, that this sequence when I see the relative parameters of this sequence, I get that the sequences of information rates are greater or equal than 1 minus delta 1 minus 1 over A of Q. And this is what I wanted. So I didn't do a proof, of course. I just put some things that tell us, how to build sequences of long codes. We have to think on the set of rational places, and I can use it all of them, and for example get an element here which is something with another place. If this is a place of degree greater than 1, then it's not going to be the support of this divisor and the, of this divisor are going to be different. Or if I want, I can do it like this, that remove one of these places, remove one of these rational places, and use it here for the divisor G. And so with this kind of construction, we get a lower bound for many functions. So we actually know that it has to be a sequence of codes with those parameters. And in particular, if we use the case in which we know A of Q, the case of Q being square, that is the Fassmann-Bladut-Singh bound, if we have that Q is a square bigger than 4, because we need A of Q be bigger than 1, then we can replace the actual value of A of Q, which is square root of Q minus 1, and what we get is that the Manning function is bounded by 1 minus 1 over square root of Q minus 1 minus delta in the interval between 1 and square root of Q minus 1. So in this interval. So we know that we can build a sequence because actually there are examples, for example, using towers of function field, as I said in the reference that I gave you at the beginning after the break. We can build a sequence of function fields that we can, for each extension in that function field, build explicitly code, and the parameters of those codes are going to satisfy this. And so with that specific construction, we get a lower bound for Manning function. So if we came here again to the case of the case that we were studying, this is exactly what I told you. In the case of Q equals 49, is the first time where we achieve a better result than the Gilbert-Bachamov bound. Look that here, this is the Gilbert-Bachamov bound for Q equals 49, and this is the Fassmann-Bladut-Singh bound. If you look carefully, well, maybe you cannot tell from there, but here we have an interval in the middle in which the Fassmann-Bladut-Singh bound is better. Of course, not in those parts, but in the middle here, if we have like a balance between the relative minimum distance and the the information rate, then we have an improvement here. So we can see it in, for Q equals 64, which is better. Then we see, well, I don't know if we can see, if you can see it from there, but you can just draw this bound because are really easy to draw. And so you see that we have something here, and this bound, what it's saying is, well, actually, Manning function is above this thing. And so before we knew about this bound, we thought that the better thing that we could achieve was the Hilbert-Barchamon bound. But now, having a bit better bound, we can assure that we can build a sequence of code such that the relative parameters tends to that element. Okay, so to end, actually, what I want to give you is one way of getting this construction that I used to study when I was doing my PhD. And the book of Stichteno has, the second edition has a complete chapter about that if you want to study that things that are towers of function fields. And I won't say a lot about these towers, but maybe you will find the example that you want here. Of course, that you could take an entire course about towers of function fields, but at least we are going to have some definitions and one result. So one way of getting lower bound for Ihara constant is through the study of asymptotically good towers of function fields. And so the definition is a tower of function fields over FQ. It's an infinite sequence of function fields. Let's call it F0, F1, of function field over FQ over the same finite field FQ, such that where first all the fields are strictly contained in the next one. So I have that F0 is strictly contained in F1, strictly contained in F2, and I have to go on like this. The second is that all the extension, if I look at Fi over Fi minus 1, this has to be a finite, of course, because both of them are finite extensions of the rational function field because they are function fields, finite and separable. This is for all I. The third condition is that if I look at the sequence of genus, if I look all the genus of each function field and I build the sequence of that tends to infinity. The sequences of genus of Fi tends to infinity as I tends to infinity. And we have the extra hypothesis that we can put it or not because we were assuming that was happening always for a function field, that FQ is the full field of constant of all the function fields that I'm working with. I will put it here, but we were assuming this for every function field. FQ is the full constant field of each Fi. And so for towers, what we know is that if we define the limit of the tower, that always exists is the limit for I tending to infinity of the number of rational places of each step in the tower over the genus. And you can say me, well, why do you put the limit? Why do you know that this is actually something that we can compute? Well, you can find the proof on the book also. This is a monotonous sequence, and it's bounded, so the limit exists. And this is defined as the limit of the tower. And of course, this limit is always bigger or equal than 0. And a natural upper bound for this limit is the Hara constant. Because for the Hara constant, we were looking the maximum number of rational places that a function field of genus G can have. And here we are not taking the maximum number over all the function field, but we are taking the number over one finite field, function field. So this is a lower bound for Hara constant. And now we see that one way of getting lower bounds for this is getting this kind of sequences in which this limit is positive, because if this limit is 0, then I have a trivial bound. So I want towers of function field such that the limit of the tower is non-negative. And when this happened, we said that the tower is asymptotically good. In this case, we said that F is an asymptotically good tower. And in the case where lambda is 0, we say that it's asymptotically bad. In the case of the square of q being a square, that we know that a of q is exactly square root of q minus 1, if we can build a tower such that the limit is exactly square root of q minus 1 for q squared, then we said that the tower is optimal. You say, well, this is the best that you can achieve, having the limit equal to square root of 1 minus 1, of q minus 1. And so, I don't know where I had the last page. No. Here, no, it's here, sorry. So our last example, that is not going to be a complete example, but you will know a bit about this, is an example of how to build a tower in order to then be able to construct the sequence of codes. And so, for example, we choose Q, a finite field fq squared, be a finite field with q bigger than 2. So q squared is bigger than 4. That was what we needed. We had it as a hypothesis on the bound. And then we consider this equation, y to the cube plus y equal to x to the q over x q minus 1 plus 1. This equation defines an asymptotically good tower of function field. I'm going to tell you how. Same asymptotically good tower. And this was proved by Garcia and Stichtenov. In 2007, and they have a lot of equations defining asymptotically good and asymptotically optimal towers also. That means that if I look at the limit of the tower, I have a non-zero bound. The limit is something which is not zero. But how, with this equation, I build a sequence of function fields? Well, I start with my first step on the tower to be the rational function field. This is the example that we were working the whole week. So I put the first field in the tower to be this one, as q squared. Sorry, I'm always working over q squared, and the equation is going to have q. Well, to build the second step, so here I have fq. Fq, I just build fq squared, and any finite extension of fq squared is going to be any finite extension of the rational function field over fq squared is going to be a function field. So in particular, if I pick this as the first step, I'm okay. The second step is going to be this same field, but where I add a root of this equation. So I let's say that this is x0, a transcendental element over fq squared, and so I add here an element x1 such that the relationship between x1 and x0 is that x1 squared plus x1 is equal to x0 to the q over x0 to the q minus 1 plus 1. And so I have here, another function field, which is fq of x0, x1. And so I do the same thing again. I put f2 to be the previous one, f1, in which I add another element such that the relationship between x2 and x1 is given by this equation. That is, x2 to the cube plus x2 is equal to x1 to the cube over x1 q minus 1 plus 1. And so I build here another step in the tower, which is f1 of x2, and at the end is going to be the same as fq squared of x0, x1, x2. And I continue like this, always using the same equation. And at the end, and after working a lot, don't believe that it is easy just to put any equation and to get a asymptotically good tower. But at the end, after working with this tower, I can prove first that this actually defines a tower. So that all of these extensions are different, that all the extensions are, of course, finite because the degree is bounded by the degree of the equation, but separable also, that the sequences of genus tend to infinity, that is not always easy to prove, and that fq squared is the full constant field of every extension. And more, they were able to prove more about this tower. When I say they, it's Garcia and Stichtenov, Arnaldo Garcia and Henning Stichtenov. They proved that for each step in the tower, the number of rational places was bigger or equal than q to the I minus 1 times q squared minus q plus 1. Well, they also had the expression for the genus of this for each function field, which was q I over 2 minus 1 square if I'm on an even step, and q to the I plus 1 over 2 minus 1, well, something else that depends on the step that I'm having if I'm on the odd case. So if I'm on an even step, I have one expression. If I'm on an odd step, I have another expression. But the important thing here is that when I see the quotient between these two things, then the amount of rational places and the genus, and I let I tend to infinity, what I get is that the limit of the tower is exactly q minus 1. And since I was looking this tower over fq squared, I know that this is exactly Ihara's constant, the value of Ihara's constant. So this is not only an asymptotically good tower, but it's an asymptotically optimal tower. And so if now I pick, if I have a description of the places here, which are the elements in the base field, in the rational function field, in which I can control which are the rational places. Because on the rational function field, that's why I always start in a tower. I could start at any point, but if I start with the rational function field, then I know how to describe rational places, because I know that the rational places inside this function field are in correspondence with the monic irreducible polynomials of degree 1 or the place at infinity. So now that if I have a description of these elements, I can, for example, left this one, that I believe it was the infinite there, to build the divisor GI in each step, and all of these for the PIs that were the evaluation set. And with this, I can construct explicit codes, or at least explicit in the way that I'm saying who are the places there. Not more. I cannot say, for example, I don't know if we know the base for the Riemann-Roch spaces up to some step. I think, I don't remember, but I cannot think of an example here of a complete tower in which we have the base of the Riemann-Roch space for all the steps on the towers. I know some examples that we get the basis for step 5 or 6, but not more than that. But well, you could look for that. And with these, you build a sequences of codes that you know that at the end, it's going to get a good bound for minus function, because you are getting exactly like the maximum allowed for a tower in its limits. So if we build using these divisors, the sequence of codes is going to be asymptotically good, and we could beat the Gilbert-Vershamov bound using this Fassmann-Bladut at zinc bound. So, well, that was all. I hope it was enough for you, that you, with this, are going to be prepared to look for other problems. You have many problems here. You can think on different towers and how to prove that towers are good towers. You can look for towers that were already studied, and then try to build the codes associated to that tower. You could start asking for more structure in the code. For example, the Ritz-Solomon code, we did not say anything about the structure, but we use only the elements to evaluate on the multiplicative group, and we do not use the zero, because if we use only the multiplicative group, since the multiplicative group is cyclic, then we can get a cyclic code, and that means that we have more structure on the coordinates in the word that work in a way that will allow us to have a faster decoding algorithm. And so you can try to see, in this case, in this setting of AG codes, how to get those properties and how to build codes with more structure, but fixing that extra structure, still having an asymptotically good sequence. So if you want to ask me something or you want any reference, the things that I've given to you, I can send you the paper that I already mentioned or the material I have. And let me, to end, thanks CIMPA for this opportunity to be here. Thank you for attending the lecture. Well, that's all.